Hello, my name is Iris. Thank you very much for joining me today. I will be talking about modeling splayfold rupture and tsunamis with self-consistent initial conditions from a geodynamic seismic cycle model of subduction. That's a whole mouthful. Okay, so let's start at the beginning. I'm talking about splayfolds and tsunamis. What are they? Well, if you don't know, splayfolds are folds in subduction zones that splay away from the megathrust. So this black fold here would be the megathrust, and then these would be the splay folds that splay away from the megathrust. Now, why are they important in tsunamis? Well, as you can see in this figure, where it's a bit more simplified, you have your megathrust, you have your splay fold, and the splay fold is much steeper than the megathrust. So if you have an earthquake that chooses the splay fold over the megathrust, the idea is that you can get much larger isolated seafloor uplift, which will then generate a larger tsunami. So that's why it's important to study splayfolds and their relation to tsunamis. What are we going to do? Well, we are going to add tsunami propagation and inundation model to our modeling framework that you can find in this paper we published last year, if you're interested. And we are going to apply this whole modeling framework consisting of 3 codes to splayfolds. So this is basically what it looks like. We start with a geodynamic seismic cycle model, use the output of this as input for the dynamic rupture model, and then use the output of the dynamic rupture model as input for the tsunami model. So let's start at the beginning. What does our geodynamic seismic cycle model setup look like? Well, looks like this. We have an oceanic plate and we push it with 7.5 centimeters per year towards our continental plate. There's a little accretionary wedge in between. And as input, we define this initial geometry, subduction velocity, the temperature profile, and viscoelastoplastic rock properties that are constrained by the literature on lab research. So we do this, we get our subduction geometry, we go into the seismic cycle phase where we get these slip-like events. And then for one particular event, we choose to couple that to a dynamic rupture model. But how do we find the faults, in particular the splay faults? Well, what we see in the geodynamic model is that there is a lot of yielding in the accretionary wedge. Here I'm showing you the viscoplastic strain, and all these dark colors are yielding in the accretionary wedge. So from this, we can see several geometries, and we pick 6 blind splayfold geometries. And that then looks like this. Here, for a bit better visualization, I plot the accumulated slip. And we pick these 6 splayfold geometries. And these then go into our dynamic rupture model setup, which completely consists of input from the geodynamic seismic cycle setup. So we use the rock properties, the stress field, friction parameters, and the fault geometry as input from the seismic cycle model. And we have our little 6 splayfolds plotting p-wave velocity here. So what happens then if we run this model? Well, I'm going to show you a little video. Let's hope it works. In the top panel, I'm going to show you the maximum slip rate on the fault. And then here we have the horizontal component of the velocity. And here we have the vertical component of the velocity. So let's start the video. So we have our rupture coming in. It encounters the first splayfold. And as you can see, it goes on the splayfold. It doesn't go on the other splayfold, the next one, but it does go there when there are waves going back. So if we go back a little bit, you can see these waves, they hit the surface, they are going back, they are reflected, they impact the fault, and then it goes from the top towards the bottom. So that's actually quite interesting. It's not activated when the main rupture crosses the splayfold first, but it is activated when the reflecting waves encounter it. And a combination of those 2 factors activate these splayfolds here that you can see. And a lot of the seismic energy then stays there. Okay, so all the splayfolds get activated. And what this looks like on the megathrust, if we look at some slip rate evolution plots, we can have a look at what it looks like. So this is our model, just for comparison, from the paper in 2019. We show here the distance along the fault. So this is near the trench, and this is more towards depth, and this is with time. And without splay faults, the rupture looks like this. So we rupture mainly towards the shallow part of the fault, and we see lots of complications in terms of reflections and waves impacting the fault once again. In the model that includes splay faults, and they're indicated here by the vertical lines, it looks kind of similar, except that you can see that the slip rate is lower overall, and we will see in a bit that that is actually due to the splay fault. So this is what happens on the megathrust. We can also look at what happens on each individual splay fault, and here we see what happens for each splay fault. So this is splay fault 1, 2, 3, 4, 5, 6, 6 being the deepest, largest splay fault. So as we saw in the video, all the splay faults rupture, and that can be due to the first main rupture front that encounters it and it's immediately activated, such as is the case for splay fault 6, the deepest one, and the first one the rupture encounters. It can be dynamic stress transfer and stress changes induced by reflecting waves, such as what we saw in the next splay fault 5. It was activated from the top by reflecting waves from the surface, and then it ruptured down dip. Okay, so what does this do in terms of slip? Well, in terms of slip on the megathrust, we can clearly see, again, these vertical lines are the splay faults, that when it goes on the splay fault, the slip is slightly less on the megathrust, and the slip is actually accommodated on the splay fault. So then you can say, okay, so wasn't this this whole thing about surface displacements, them being higher and things like that, the importance for tsunami genesis and the height of the tsunami? Yes, exactly. So we can have a look at the effect of splay fault rupture on surface displacements. So here we see, again for comparison, a model without splay faults in green at the moment, and you can see it's quite uniform, maybe 5 meters, the final vertical displacement. But if we then plot our model including the splay faults, it looks like this. And we can see these big peaks. And if I then plot where the splay faults are, you will see these peaks of vertical surface displacement correspond to rupture on the steeper splay faults. So what happens then in the actual tsunami? Well, in order for that, we will couple the dynamic rupture model to a tsunami model again. And our initial tsunami model setup looks like this. It's a 1D model, and we have an initial sea at rest. This is our topography. And as input, we use the time-dependent surface displacements of the dynamic rupture model. So if we run that, we have the following results. So first, again, a model without splay faults for comparison. Here we have the distance from the trench. So here is the beach, so and then we have time. So we're plotting sea surface height here, so you can see how the tsunami evolved. And we can see a rather uniform, big wave going towards the beach. And that's that. In the case of the splay faults, we can see these expressions of the surface displacements we saw earlier, in that there is a big wave here with a high amplitude that goes and reaches the beach first. And then there are lots of smaller peaks that reach the beach afterwards. And these kind of all interfere with each other when they get towards the beach at roughly the same time. So if we want to look at that in time, we can look at several places. So in the ocean, it looks like this. Again, green is the model without splay faults, and blue is the model including splay faults. And if we look at the coast, we see that there's 2 flooding episodes. So first, we have this large, high amplitude tsunami peak, flooding episode 1, which corresponds to this largest splay fault the rupture encounters first and produces the most surface displacement on. And then later, we get all the interfering waves with each other that create a second flooding episode here. And so this is with time again, and then on the beach, we can see it clearly as well, these two peaks of water on the land. So what have I shown you in this presentation? Well, we can now model tsunamigenic earthquakes and the actual resulting tsunami over a large range of timescales by combining a geodynamic seismic cycle model with a dynamic rupture model with a tsunami model. So that is pretty cool. And this kind of shows what our modeling framework can do. Then we actually apply this to splay faults, and we see that rupture can occur on multiple splay faults during a single event. And this drastically affects the surface displacement and the resulting tsunami, because where you have rupture on splay faults, you get larger surface displacements and larger tsunami heights. And with that, I want to thank you for your time, and I hope you have a lovely day. Thank you very much. Bye.